Please.
Yeah, so, right. Okay. Right, so good afternoon or good morning, depending where you are, everybody. Well, yeah, so welcome to my talk. I would like to talk to you about this uniqueness for the fractional Calderon problem with quasi-local perturbations. Some things need to be explained here. Just in order to be sure, you can see my cursor, right? So you can see me pointing at stuff on the...
Right, we can see it.
All right, great. So some things need to be explained, particularly what these quasi-local perturbations are. In principle, I mean, this talk would contain also an introduction to the Calderon problem, but probably this is not very needed at this level. Anyway, we'll just say something about this in order to all be on the same plane, also because, I mean, some motivation for this talk comes from other perturbed versions of the fractional Calderon problem. Then I will tell about what these quasi-local perturbations are supposed to be, give some examples, and we'll see that actually there are, I mean, among the others, examples that are easily expressed in mathematical form, in mathematical closed form, if you want. And then I will be able to talk this quasi-locally perturbed fractional Calderon problem, which, I mean, first we will define the problem. What does it mean? I mean, through well-posedness definition of the end maps, I mean, usual stuff. We'll see an Alexandrian identity. After having seen what the main results should be, we will see, I mean, what happens for the proof. Of course, we won't be able to give a complete proof. That would take some more time, but we'll see in the main points, and in particular this unique continuation property, which in this case is not completely trivial, as one could say that it is. I mean, in this case, it's not immediate how one can reduce that to the case of the fractional Laplacian. And then we will see that because of some other stuff going on in this for this operator, for this perturbed operator, we will need not only a qualitative Runge approximation property, but also a quantitative one. We will see how essential this is. There will be some geometric conditions to be respected. So there is a little bit going on. And maybe we can see also the proof of the main theorems if time allows. Right. So let's go fast through this introduction, since the audience is very expert on the topic. You know, of course, about the classical Calderon problem. We have just a conductivity inside a body, and we would like to be able to tell what the conductivity is by measurements performed without invading the body. Since the operator here is local, just this conductivity equation, we would like to perform measurements on the boundary. And these measurements, of course, are expressed can be expressed, for example, in the form of this DN map that takes voltages F on the boundary or part of the boundary and sends them to the normal component of the current on the surface of the body. Okay, so of course this should be blue and not B. Right. So we create this DN map, and the question, of course, is whether we can recover gamma from lambda gamma, since lambda gamma contains information about what gamma is. And after a usual reduction, a fractional, a Liouville reduction, one would have that this problem can be expressed in terms of the Schrödinger equation. Right. This just as a fast introduction to what we are going to. Many results are known. This, as you know, I mean, many authors of these papers are based on CGO solutions, right, through this integral identities way. And of course, I mean, you show also stability with a logarithmic modulus of continuity. This will be important in a little bit. Reconstruction can be shown in some cases. Partial data have also been studied. And in the results in dimension n equals 2, of course, you know, these are completely shown. I mean, for also for potentials coming from LP with a certain P up to a certain point. This is known stuff. And also partial data, the problem is solved in this case. Right. But let's go to the fractional Calderon problem, in which we consider not anymore the classical Schrödinger equation, but the fractional Schrödinger equation. So we have a fractional Laplacian instead than a classical Laplacian. So you see why I talked about this level reduction, because of that level reduction, we can talk about classical Schrödinger equation as in the case of the Calderon problem. Here we talk about the fractional Calderon problem when we talk about the fractional Schrödinger equation. So we don't pass through conductivity, even though we could. This is what we call the fractional Calderon problem, the problem of whether we can recover this potential Q from this Dirichlet to Neumann, from this non-local Dirichlet to Neumann map. So in this case, we give some potential F over W in the W1 here in the exterior, maybe. And this causes a certain solution U to be established over all of our N. This is of course supported on omega W1. And if we read this fractional Laplacian of UF, solution UF over W2, we've got this DN map. Technically, in between these spaces is abstract quotient spaces X. But actually, I mean, in many cases of regular boundary, we can just reduce to the idea of having some exterior values or something over omega exterior. And well, can we recover this Q from lambda Q directly in partial data, so from W1 to W2? And it turns out we can in many cases. So uniqueness has been shown for potential Snell infinity in the seminal paper by Goschal and Ullmann, of course. Regularity has been then achieved for, so also for low regularity potential. Uniqueness has been achieved also for low regularity potentials. Stability, much stuff has been considered. Uniqueness with one measurement, even reconstruction. Monetism methods have been studied by Arach and Lin, and also perturbed version of this fractional Calderon problem and be considered. Of course, I mean, I don't intend to offend anybody of the presence, but of course, this is very fast, and this is just a minimal part of the results that are known at the moment about the Calderon problem. Right. So in this perturbed version of the fractional Calderon problem, we just add some perturbations of many kinds to the fractional Schrödinger equation, which are meant to signify, perturbations in the model, right? So this could be, for example, the anisotropic case studied by Goschel and Chao, where you have some A here, some matrix A here, so the operator, the main part of the operator becomes anisotropic, and we recover Q by knowing A. Or this fractional conductivity equation studied by myself, in which you use these fractional operators in order to, to have a connection in between the ideas of conductivity equation, even with Schrödinger equation, even in the fractional case. One shows that this gets reduced to the fractional Schrödinger equation in much the same way as the conductivity, classical conductivity equation gets reduced to the classical Schrödinger equation. And then also first order perturbations, in this case by Jekic, Lin, and Ruland, in which we add this gradient term here, and we recover B and Q. So besides this zeroth order perturbation, we have this first order perturbation. In this case, S needs to be large enough. And also the fractional magnetic Schrödinger equation in various ways. I mean, I write here an example, but there have been many magnetic variants by not only myself and my collaborators, but also by Bacharaya, Ghosh, Ullmann, and Lee. Lower order nonlinear perturbations, for example, have also been considered. Particularly interesting to me is here, this is using this fractional gradient, again, by Lie and Home. And most importantly for this talk, the higher order fractional Schrödinger equation with local perturbations that I myself, Keijo München, and Jesper Mutter studied until recently, in fact, was recently accepted for publication. Well, in this case, we have just this local perturbation in the form of this differential operator, right? And we want to recover all the coefficients of the differential operator. Of course, in order for this to be a perturbation, we need the order of the fractional Laplacian to be pretty high. So we just take any real number which is non-integer, such that no locality is preserved. And we study this higher order result, and with this higher order operator, we show that all these coefficients can be recovered from the DN map. And I say that this is particularly important, I mean, as motivation for this talk, because what does one do after all local perturbations have been considered? Of course, the next thing to go would be to consider some non-local perturbation, but a general non-local perturbation is something like very ill-defined. I mean, this could be just anything. So let's go slowly, and in this talk, we start by exploring what happens if the perturbation here, instead than local, is quasi-local, in a sense that I will explain in a second. And in fact, let's define what these quasi-local perturbations are, and give some examples of them, such that we can fix our ideas. All right, so quasi-local perturbations. And these come in two flavors in this talk. There is an easy flavor and a little bit more convoluted flavor. The first flavor, the easy one, are these operators of finite propagation. Right, so these operators for which the support of U gets extended by a maximum of R, say. So if you have U that is compactly supported in some K, for example, then the support of psi of U will be contained inside the neighborhood of radius R of the support of U, so of this compact set K. And the smallest R, such that this holds for every U in HS, this operator is defined on HS, for example, this is called the propagation of psi. So for example, say that you have an operator propagation 1, this means that if you take any function supporting the unit ball, then psi of U will be supported on the ball of radius 2, independently from what U is. All right, and this kind of perturbations, this kind of operators are of course non-local in principle, unless R is 0. Of course, in that case, the support of U and the transformed U are the same, and so the operator is by definition local. But let's give an example. I'm sure you were thinking of this example while I was describing this. If you just take any K that is smooth and compactly supported, for example, on the ball of radius R, then when you take the convolution against U, and you define this operator psi just to be the convolution against K, so this function K, that is fixed, then of course this operator is of finite propagation, and the propagation is exactly R. All right, because you start from a function U, for example, as in this case, which is supported in between -1 and 1, say, and if R is 1, you will end up, if you convolute U against this function K, any function K of this kind, with something like this red function that is supported in between -2 and 2. Now this looks very easy, of course, I agree, but these convolutions are not the unique example, of course, of finite propagation. If you are interested, and if we have time, we can see others which are which I talk about in the paper. But these are not the unique example, but of course, I mean, this is what one should have in mind. I mean, this is the behavior of this finite propagation. And of course, these are non-local. So even for these very easy examples, our previous results are bound not to work, because those were only for local perturbations. As an example, of course, I mean, the unique continuation property won't work just as easily for this kind of perturbations. Right, and this is the easy flavor. A little bit more complicated, next step would be, of course, to consider what if U, for example, is compactly supported, but when you apply psi on it, so you get psi of U, this is now supported everywhere on Rn, so completely non-local, but there is some decay, right? So if you go far away from the support of U, the function is getting really small in some norm sense, all right? And there is some control. This is exactly what these quasilocal perturbations are. And the quasilocal perturbation psi has a decay function mu associated to it, a function that is positive. Oh, you cannot see this, but this is R0 plus, all right? So let's move this here. You say then this decay function mu that is associated to psi, this is from R plus to R plus 0. And so this function decays, by definition, when R goes to infinity, right? So it has got this slope behavior, right? This is associated to psi. And we have, by definition of quasilocal perturbation, this estimate. So if you look at the norm H minus S, because this is from HS to H minus S, but maybe you can also only think from like L2 to L2. If you take the norm of psi u over the set of all points that are more than r away from the support of u, then this norm is small and is controlled by this function mu r, so a function just of the distance, and the norm of u in HS. All right. Now this maybe looks a little bit artificial, but there are easy examples of this fact. For example, convolution again, but there are things that are all convolution, I swear. Convolution against a Schwarz function, for example, would be of this kind. So, for example, you start from the same u as before, compactly supported in between -1 and 1. So this function is L2, for example, and you apply psi of u, get this orange function now that is supported everywhere because this k was just Schwarz and defined everywhere. But as you see, there is this decay. So if you take, for example, the L2 norm of all the points that are more than 2 away from the support of u, so under -3 or over 3, you get to see that the function is very small. And in this case, one can associate a certain mu to this k, a certain decay function. Right, some properties of these quasi-local perturbations, or operators more in general. They will be only perturbations when we introduce the problem. Sorry. Right, so as we said, all local operators, of course, are of finite propagation because they have finite propagation equal to 0. But all finite propagation operators are also quasi-local. This is probably believable, but there is easy demonstration. This is the mu r that you should associate to operator finite propagation in order to see it as a quasi-local operator. So if psi has finite propagation is bounded, all these operators will always be bounded for other reasons. Then you can associate to it a certain decay function mu, and with this decay function, this finite propagation operator is quasi-local. So this inclusion solved. And all these inclusions can be proved to be proper, of course. So there are quasi-local operators which have not finite propagation, and the finite propagation operators which are not local. I repeat just for clarity that up to now, our results for uniqueness in the fractional Schrödinger perturbed fractional Schrödinger equation were for local operators. So there is big family of operators for which these don't hold. These are not local operators. Other properties which will be useful in our computations later on, if we get to see them, is that an operator psi from L2 to L2, which is quasi-local with certain decay function mu, can be interpreted as operator from HS to H minus S. It's useful to notice that this has the same decay function mu, also when considered as an operator this way. And also, if you start from a psi from HS to H minus S and take the adjoint, well, if this was quasi-local with decay function mu, this is still quasi-local, the adjoint, with decay function mu. This will be useful because in order to study uniqueness, we need to study both the direct problem and the adjoint problem, which has psi star as a perturbation, so it's useful then that they have the same decay function. This can be proved as a lemma. Right, and now eventually after a little bit of presentation, we are well with time, we can start talking about this quasi-locally perturbed fractional Calderon problem. And I mean, won't stop on all those details, which I'm sure will bore you, and I will just go to the interesting parts. Definition. We have this fractional Calderon problem, fractional Schrödinger equation with this quasi-local perturbation. Now, actually, for the well-posedness part, we don't need this to be quasi-local. Just bounded and with a certain approximation property in L2 is enough. But, I mean, there is no need to make this distinction at this point. Just let's think of this as a quasi-local perturbation all the time. Well, and what happens is that we define this bilinear form, usual way. This is non-symmetric, of course, because if we take W and B and we invert them, this term will create some problems. But then we will study also the B psi star. Anyway, this bilinear form is bounded, it's coercive, this can be proved, it's a lemma. And therefore, we have a well-posedness result, which is similar to Gauss-Salo-Ullmann. So if we are outside a certain set of eigenvalues, which is luckily couptable, then we have that this problem here that we propose has got a unique solution independently from what large f, small f we give, if they come from the right families and from like space of functions. And also we have this estimate. From now on, of course, we assume that 0 is not a Dirichlet eigenvalue for this problem, as one usually does, so that this problem is uniquely solvable, the direct problem. We need this because without that, we wouldn't be able to define the DN maps. So the DN maps are defined the usual way. This lambda psi is defined as this V psi operating over G, and this, which is the solution corresponding to F in the direct problem. So this P is for Poisson operator, of course. We apply this Poisson operator psi on F, and we get unique solution. It is granted by the well-posedness result. And in this way, we can define the DN map, usual way. And also there is this adjoint DN map, which does the same thing for the adjoint operator. And it turns out, of course, that the adjoint of the DN map is the DN map of the adjoint. This operator is this property here is very useful, because with these we can have our Alessandrini identity. Of course, I'm not proving either this DN map stuff, which is just lemma, neither this Alessandrini identity, which is just computation, and I'm sure you believe me. So this Alessandrini identity, it looks like just what you would expect. So you have this difference of DN maps on one side, and on the other side, the difference of the operators. And you have, of course, solutions corresponding to exterior values F and G, what you are computing the DN map on, to the direct problem with psi1 and the adjoint problem with psi2. All right. Then, of course, now you have perfectly in mind what we want to do in order to achieve our solution, right? We would, our proof of uniqueness, I mean. We would like to be able to say that these two functions are anything you like, just that essentially any function, maybe from, in this case, HS, I believe, can be estimated in terms of these solutions to the direct and adjoint problem for these quasi-local perturbations. So you would like a Runge approximation property. There will be a problem. I mean, if you only have a qualitative Runge approximation property, there will be a problem. Your proof in the end will not work because this operator here, the difference is a non-local operator in principle, which will break down the machinery. Usually in all the other stuff that I have had occasion to read about this perturbed Calderon problem, this difference appearing on the right side of the Alessandrini identity always was a local operator. But in this case, it is not. So we will have problems. But let's come back to that later. First of all, we need the Runge approximation property, the qualitative one. And for that, we need unique continuation property. Oh, yeah, okay, so, pardon, I mean, sorry, I should have stated here the main results first, but I'm sure you know what they look like. The DN maps coincide, then the two perturbations also coincide. And we have two main results, one for finite propagation and one for quasi-local perturbations. Right? These are, of course, I mean, the result for quasi-local perturbation contains the result for finite propagation, at least, I mean, if all geometric conditions and stuff are achieved in both cases. But the proof for finite propagation is much easier. So it was worth, in my opinion, to state it separately. It does not require all the tricks that are needed for quasi-local perturbations. And actually, it kind of indicates what the needed tricks will be for the more difficult case. And in fact, you see here that something is different. I mean, here we need some geometric condition. We need W1 and W2 to be far among themselves and from omega. So there will be a number, and if W1 and W2 and omega are far enough from each other, farther than this distance from each other and from omega, then this result will work. And this makes sense because this finite propagation, I mean, this number is related to the propagation speed, say, right? This is logical, and now we'll see, actually, we will be able to see the proof of this completely. And instead, in this other case, there are some things that are different. For example, we need this psi1, psi2 quasi-local perturbations to have enough decay, this condition star just is a condition of how fast this mu function decays. Remember that this mu decay function here was saying how fast this quasilocal perturbation is like vanishing when you go farther away from the support of u. Even though this perturbation is never zero, in principle, there is this decay function mu. And here with this star condition, we're only saying that this mu is decaying fast enough. How fast is an interesting question. In fact, we will be maybe able to see later how much. The interesting thing here is this geometric condition. I need W1 and W2 to be unbounded. Forget about this other condition, which I believe can be eliminated, and I just added for clarity of exposition. But the important thing here is that the sets on which you are measuring need to be unbounded. And this will come out clear. I mean, it will be clear why this is the case during the proof. But for the rest, this uniqueness result is what you expect. The n maps coincide, and so the operators coincide. The perturbation operators coincide. Right. And in order to see why we have to make these assumptions, we need to turn to the proof of unique continuation. So let's start from unique continuation property for these perturbations of finite propagation. It's easy, and in fact, we get to see a proof by picture. So assume that U is supported over omega, essentially, is HS tilde of omega, and assume that the operator vanishes on some set W, which is in the exterior of omega, and actually it has got the property written here, which says essentially that like it has got a subset, a non-empty subset, which is far enough from omega, farther than the propagation of psi. Then in this case, U is 0. Essentially, we're saying U is supported on omega. The operator here is 0 over W disjoint from omega and far enough from omega. Then U is 0 everywhere. And why? Because you see, if U is supported over omega, then psi of U will be supported a little bit farther away in this orange set. So this orange set is where psi U here is supported. Psi U is 0 outside. But when we take W, now this W is the set where the operator is 0, and it also contains a subset W1 on which the perturbation is 0, right? Because it's outside of omega, outside of the support of U, and it's outside also of the support of psi of U. Then what does this mean? In W1, the operator vanishes, the perturbation vanishes. Well, this means that fractional Laplacian must vanish over W1. W1 is also a set where U vanishes because it's outside of omega. Then in this set, both U and W and the fractional Laplacian of U vanish, which means by the unique continuation property for the fractional Laplacian that U must be 0 everywhere. So you see the very cheap trick that is happening in this proof. We are just assuming that we can go far away enough from the set where the perturbation is supported. We don't see the perturbation anymore. It's if the perturbation didn't exist. And so we can recover a result by means of the unique continuation property for the fractional Laplacian. It was easy. But if we want to prove unique continuation property for the quasi-local perturbations, we will have some problem, because in that case, it's not true that we can go far enough and we get the perturbation disappears. Right, because the perturbation in principle is non-zero everywhere in Rn. It's small, okay, but it's non-zero everywhere. So we need to do something else. And let me have some construction before actually we go to that proof of unique continuation. So we take the stability lemma that comes from Rule and Salo, low regularity and stability, just right here, because if I write only Rule and Salo, that could be 20 papers. So low regularity and stability. And so this says that if you have, let's see, of course, I mean, that was not done for a bounded operator, but let's see now how does this look like, this result. You take a psi that is bounded from L2 to L2, say, and of small norm, this is the operator norm in this here, of smaller than a certain m, say, and then you consider this equation here, this perturbed Laplacian equation, fractional Laplacian equation, in which you introduce W as a unique solution with exterior value 0 for this inhomogeneity V, which is some L2 function of norm 1. All right. Then you have this estimate. Actually, I mean, the result means that you can find C and sigma, two constants depending on omega, W, N, S, M, on all the constants and geometric parameters of the problem, such that you can have exactly this estimate. I mean, you can find C and sigma such that this logarithmic estimate holds. And this estimate says that the H minus S norm of the inhomogeneity can be estimated over omega by a logarithmic modulus of continuity of the fractional Laplacian of the solution W here in H minus S norm of W, W being a set that is far away from omega, right? Right. Actually, as I was saying, the stability lemma was shown in Ruland and Salo 2020 here for local perturbation Q here. But if one goes and shows the perturbation, sorry, the calculations, and these are shown, in fact, in the paper I'm talking about, one sees that this result immediately extends to any bounded perturbation. And I mean, the C and sigma will depend just on how large this bound is. Because in fact, I mean, the local nature of the perturbation here, they would have had a classical, well, they would have had here a fractional Schrödinger equation, but the classical type, the one with a perturbation is just QW, right? That the local nature of this Q was not shown in the proof, and this does go through easily. Well, with this stability lemma in mind, take on omega, right? And take a W, which is now unbounded. There is no limitation, it can be unbounded in the stability lemma. Take an R that is larger than 0, and take the set which is R away from omega. So this orange set would have continued, but then I could have not written here. So you see what I'm saying here. And define this part of W as WR. If W is unbounded, this WR is non-empty, right? And it's always non-empty, and it's also always open by the definition of this neighborhood of radius R. Well, for this omega and this WR, we can find constants C and sigma here, such that an estimate like this holds after we've fixed N, S, and M. All right. So we fix omega as omega, WR instead of W, N, S, and M, whatever we like, and we're able to find C and sigma such that this estimate holds. This is what I'm saying here. Of course, this now C and sigma will depend very much on what M is, and of course also on R, because WR is depending on R. All right, and these constants will be such that the estimate gets worse and worse as R goes to infinity. If R goes to infinity, WR is getting very far away from omega, and so the estimate here gets worse and worse, which means that C grows, and if you just look at the behavior of this function, that sigma goes to 0. Actually, how C and sigma behave as R and M change is also a relatively interesting question, which is studied in this paper, in the appendix of the paper I'm talking about. Well, but with this construction in mind, we can turn to the proof of the UCP for the quasi-local perturbations. Yeah, still enough time. Right. So what does this UCP look like? Say that U is supported on omega, that the operator is 0 on W. Now this psi is the quasi-local perturbation. And say that W is, where it's written here, it's unbounded. Also say that Q decays fast enough, so as fast as to satisfy this equality, this limit here, for some M larger than 0. Then in this case, we have that U disappears everywhere. Now, this is not so trivial. So you say that U is supported in omega, this operator is 0 on W, and this psi has a decay function mu that decays fast enough, actually pretty fast if you look at the behavior of this function. Then in this case, you have that u is 0, but you need w to be unbounded. Let's see why. Well, condition start requires a fast decay from mu, and we agree. Then we can also see how fast that needs to be. And you see, we can get this quasi-local estimate now. Because if we estimate the fractional Laplacian of u on this set WR in H minus S norm, well, since on W the operator is 0, this is the same as estimating the norm of the perturbation psi mu. But this set is also farther than R from the support of u. Therefore, by the quasi-locality of psi, this can be estimated in this way. And here we have that the fractional Laplacian of u in the set WR is estimated in terms of the norm of u and this mu r function. This mu r function that is known to decay quite fast. Why do we need this? Because you see, if we take just w to be this scaled version of u, our function u, and v to be defined in this way, then w will solve this problem, which means by the stability lemma from Ruland and Salo that this kind of estimate holds actually for any m larger than 0. But then, I mean, just by belposeness of this problem here, we also have this part of the estimate. So here we can estimate w in terms of this fractional Laplacian over the set WR in a logarithmic modulus of continuity. Let's add our quasi-local estimate, and instead than this, we have just mu r and the norm of u in HS. Notice that now this guy here depends, and this unique part that depends on r. So we can easily take the limit here for r going to infinity. And that makes sense because WR is unbounded. So even if we go with r to infinity, there is always some WR. WR is not getting empty. And since we have, by assumption, that this goes to 0, well, now it's easy. You see that W actually is 0. And so U is 0 by this definition. So U is 0 everywhere. So you see, actually, I mean, what is happening here? In the stability lemma by Ruland and Salo, we get some control over, essentially by well-posedness, over the HS norm of the solution by in terms of the H minus S norm of the fractional Laplacian on a certain set. Okay, and now this quasi-locality here, I mean, this would say that if R goes to infinity, this is getting very bad, but actually mu decays so fast that this actually goes to 0. All right, even if CMR and sigma MR are doing their best for this to go to infinity, mu R decays so fast that it goes to infinity, it goes to 0. All right, so for a particular class of quasi-local perturbations, we do have this UCP, at least in this way. This is essentially the same trick as we were doing for finite propagation, but now we need to do like a limit process because there is never a point in all of our end in which, in principle, the perturbation is disappearing. This mu r needs to go to 0 pretty fast, and I again say that we later will see how fast. Now let's use this UCP. Okay, like I say, with this UCP we prove Runge, and this has nothing special to show. I mean, in fact, I have not included a proof of this Runge approximation property because it goes as usual. It's a Stamp-Banach. Okay, and it goes through because the UCP goes through. If we assume that the good assumption for UCP hold in finite propagation case and in quasi-local case, and then we will have that the density result. All right. Here we take L2 just for simplicity. These computations get a little bit more difficult, so we take from L2 to L2 instead an HS H minus S as usual. But this L2, this density in L2 is more than enough. Actually, in the end, we only need density in principle in infinity compactly supported. That's the kind of function we want to approximate. Right. So this qualitative Runge works without problem. And now, with this qualitative Runge, we can prove the main theorem, at least for finite propagation. Let's see the proof of this part for seeing why for quasi-local perturbations it won't work. You see, again, proof by picture. So we have omega, W1, and W2. And by our assumptions, if you remember, we are asking them to be far enough from each other. Now, this enough is quantified to be exactly the maximum of all the propagation of psi1 and psi2. So psi1 and psi2 are a finite propagation. They have got two propagations that are two real numbers, positive real numbers, otherwise they would be local. And it's required that this p is larger than the propagation of this, the largest of these two propagations. And we require omega W1 and W2 to be far away from each other, more than this. You probably see where this is going. Because you see now, if you take neighborhoods of radius p, they do not intersect each other. Well, the neighborhoods intersect, but the neighborhood of omega doesn't see W1 and W2, and so it goes for the other ones. So we just take our assumption that the Nmaps coincide, use the Alessandrini identity, and we have these, very nice. Now we take this F1k and F2k, which are the exterior values defined over W1 and W2 to be such that they approximate to functions we like, V1 and V2 over omega. So for a good choice of F1k and F2k, we get to approximate V1 and V2 over omega better than R1k, R2k. This is our qualitative Runge result. And now see what happens. Supports apply, I mean, particular supports resonance apply. We are able to go from this line to this line because even if we take psi minus psi2, psi1 minus psi2 of F1k, that as so much is defined inside the light blue ellipse here, the light blue set. So in particular, it doesn't touch omega. So in particular, the product of that against V2 and R2k, which are defined over omega, is 0. And is 0 also against F2k, because F2k is defined over W2, and it also doesn't touch W2. And so we can eliminate F1k from here. The same way we can eliminate F2k, and we end up with this. Now we just send k to infinity. We say we make the approximation better and better. The rests here disappear, and we end up with this guy, which of course is saying exactly, given the arbitrarity of V1 and V2, that psi1 is psi2. And here we have the main theorem for finite propagation. Everything works, even though we have the fact that this operator is non-local in nature, because the non-locality is just of finite propagation, and because we decided our measurement set to be far away from each other and from omega, then this doesn't create a problem, and we have that the perturbations coincide. All right. And what if now we try, at first try, you see in the title, what if now we try to do the same thing, but for the quasi-local perturbation? You see, W1, W2 are now unbounded. Otherwise, we have no idea how to prove Runge for the moment. And we have here the same proof, we have written here the same proof we had before. Let's see if it goes wrong. Of course, it goes well here because we have the same assumption that the maps, the same Alessandrini identity, the same Runge approximation property. So up to here, no problems. But this step will not work because if we take psi1, say, of F1k, that is defined on all of our n, in particular is defined over omega, it is defined over W2 in principle. So we cannot take F1k here away because it sees all these objects on the other side. Sees these two which are over omega and this one which is over W2. We cannot take F1k away. And we cannot go here. What if we just take now from this one k that goes to infinity? That also doesn't work because R1k and R2k are going to 0. All right. But F1k and F2k are getting wilder and wilder over W1 and W2. And so there is no hope here to just recover as before psi1 minus psi2 of V1, V2. Right? That will not work. So we need something more. In particular, we need some control over this exterior datum fjk. And this some control here is expressed in the terms of quantitative Runge approximation property, right? So there is this result here that is part of this one, I would say, of the main results of this paper I'm talking about, which is saying that if we have psi, quasi-local perturbation, which is bounded as it always was of some m, and also we have a decay function mu that decays fast enough. This star condition was the fast decay, fast logarithmic decay rho mu. Then if we want to approximate some v, we get from some v from hs tilde of omega, for example, or L2, that's the same. If we want to approximate some v, we can do that with a certain f epsilon that is defined on some w r epsilon. So this is now a set containing w, right? That is r epsilon away from the support of v, so it's r epsilon away from omega, as in the picture we have seen before. And this r epsilon is a number that depends on epsilon in such a way that when epsilon goes to 0, r epsilon explodes. It will explode real fast, but it's not a problem. We can find then, if we want to approximate v, a certain exterior value of epsilon defined on this faraway set, such that if we take the solution corresponding to this exterior value, this is similar to v, more than epsilon. But what is more interesting, if we look at what this f epsilon looks like in norm of the set where it is defined, this is also, how to say, estimable and can also be estimated in this sense. Now this looks fishy. I mean, you know that this should explode, right, if epsilon gets very small. But this is the case. This is not saying anything bad. This is actually saying that we have no estimate if epsilon gets really small. Because if epsilon gets small, r epsilon gets huge, which means that mu over epsilon gets really small, right? Because mu vanishes at infinity. So if r epsilon is very large, mu r epsilon is very small. And now this delta minus 1 is negative by definition. So this number here is getting huge when epsilon goes to 0. So if the perturbation, if the approximation here is done in such a way that the solution looks really like V, then the exterior value is getting real wild. But the interesting thing is that we can do this in terms of this decay function here. The interesting thing is that you know that normally here we would have some exponential, right? And instead, here we can define this in terms of our decay function for the quasilocal perturbations, which is very good, because then it would, this means that we can use that in our computations, and that will get very easy. And why can we do this exactly with this decay function? Well, because we have this condition star. If you recall, this condition star was saying essentially that mu was exploding in an exponential way, right? Because that had a logarithm inside. And so the exponentiality of this estimate is contained into the definition of mu, because by assumption, we ask that it satisfies this condition star. Very well, there won't be time to prove this, and I assume there wouldn't be time, so there is no proof of this written here. But we could say some words if you are interested. This comes from the same paper, Ruland-Salo, Low Regularity and Stability, from which I'm taking with full hands. And in fact, because of star, you see that the behavior of this mu is exponential, right? So if we have this quantitative Runge result, which we do, then we can do something, and we can actually prove the theorem. I've got something here first about this geometric assumption. Yeah, so let's see also a second this thing. We have enough time. Yeah, right. So if you recall, there was also some geometric assumption here. What is it? Yeah, here it is. So there was also some geometric assumption. Besides W1 and W2 being unbounded, which is required for having UCP for quasi-local perturbations, we are also asking this particular thing here, which now we express. This thing, as I said, is probably not needed, or at least not in this very strong form. But I decided to put it this way because it's not the main point of the problem, and also because that makes things much easier. And it's also not very far away from maybe a real situation. I mean, there are sets which do that thing. So we require that if we take x1 from W1 and x2 from W2, they are more distant from each other than they are from omega. All right. So if this is, for example, the situation, if you take x1 from W1 and x2 from W2, their mutual distance is larger than the distance of x1 from omega and x2 from omega. And this, for example, can be established if W2 belongs, well, is contained in the polar cone of W1, which is defined in this geometric way. All right. This also means for this symmetric condition that W1 is contained into the polar cone of W2. If this is the case, so if W1 and W2 are chosen in such a way that they are in each other's polar cone, then this thing here will be satisfied. It's easy to prove that geometrically. And also, for the nature of how these polar cones work, it is enough for W1 and W2 to be in opposite orthants or quadrants in this particular picture. So if W1 and W2 are in opposite orthants, while the origin belongs to omega, then this is enough, this geometric condition holds. But I repeat, this geometric assumption is probably not needed, it just makes things easy. And with this in mind, we can now go to the proof of our main theorem for quasilocal perturbations. Fix the ideas that V1 and V2 are of norm 1. It makes computations easier, and then we remove it. Then, you know by the quantitative Runge that you could find two sequences of functions, right? F1k and F2k, the exterior data, which are contained into subsets of W1 and W2, which are getting far away from omega of as fast as Rk, say. And they are done in such a way that when you take the solution corresponding to F1k, that is close to V1, closer than k, I don't know, to -1. And actually, this F1k can be estimated by this number, essentially, containing this mu function. So this is the estimate we had before. And also, we can do the same for P2, right? Very well. And if we have these two things from the quantitative Runge now, we are in a better position than before, because we can do the same estimate, essentially. This we don't need yet. And we can do the same estimate, essentially, but we now have some control over what F1k and F2k are doing in terms of this mu function. And now, by the geometric conditions that we have assumed, if we notice, omega and the support of fjk are by definition farther than rk, because f1k is defined over this set, which you recall is rk away from omega. So the distance in between omega and the support of each one of these fjk is larger than rk, which means also that the support of f1k and f2k are farther away than these, because this is the distance in between x1 and x2, and this is the distance in between x1 and omega and x2 of omega, in what we were saying before. Right. So everything is farther away than rk, and this is good, because now we can estimate the term that was creating problems before. So the proof will go exactly as before. Assumption of the nmap, Alessandrini identity, and then approximation, Runge approximation. So we get this psi1 minus psi2, f1k plus v1 plus r1k against f2k plus r2k plus v2. All right. And then we have to estimate those terms that were creating problems. They are of this form. So let's see if we can estimate these ones. This is 1k against all the rest of the stuff that we had. Well, we can estimate that, because since f2k plus v2 plus r2k is contained into omega, support of these two guys, union support of this guy, then we have, just by Hölder, this fact here. We can use here this two, because the union of these two sets is the support of this guy here. And now we go estimate. Right. This one, just triangle inequality, very easy. And this other one, well, this other one, now we observe that since, let's see, since f2k and omega are far away from each other, more than rk, then we know that this set is contained into the set of all the stuff that is more than rk away from the support of f1k. I know this is a little bit convoluted, but that would be easily expressed with a picture, which is essentially the same one we had before for finite propagation. This set is contained into this because of our geometric assumptions. And now this set is exactly the one over which we are able to estimate an object of this kind by quasilocal property. And so we do that, and we can estimate this object here by mu rk and the norm of f1k in L2. Now this looks good because this one goes to 0, but these can be very wild. Also, we estimate, well, this is 1 by definition. With this, we can estimate by k minus 1. It's written here. And this guy here, we can estimate by this. So we get this particular mixture of estimates. And eventually, we estimate this last guy in these terms. All right? This is allowed. L2 is over n, but this function is defined over this set, so it makes sense. And so since this is delta minus 1, there is a 1 here, we get just delta. This is the final estimate. And now let's send k to, well, to infinity. And let's see what happens. K goes to infinity, this guy disappears, this stays 1, of course. And here we have, let's see, mu r k to power delta, this delta is positive, mu is going to 0. So this one is going to 0 against these two guys. These two guys don't create problems. And when we have just these, we have something like mrk to power 2 delta minus 1. Well, now we went and used the fact that we were saying before delta larger than 1/2. All right, if we do this, then we see that by k going to infinity, this goes to 0. Oh, well, if this goes to 0, this means that we can estimate this guy. So you see, effectively, now we are saying that even if these F1Ks are getting very wild, since we have this perturbation to be quasilocal, a particular flavor of non-local, and since the decay of this function is very fast by assumption, I mean, the decay of the decay function of this guy goes to 0 very fast, but it's still non-zero everywhere, so we're still talking about a non-local perturbation. Well, then, even if F1K and F2K are very wild, we can still estimate this. And we get still that this term that created problem goes to 0. But then we can say that psi1 minus psi2 of v1, v2 is equal to 0. And so psi1 is psi2. The proof is complete. And also, I guess the time is over. So let's go to questions maybe. And I thank you in very languages. The place where I am now, the place where you are from, and the people who pay me. Thank you very much.
Thank you very much, Giovanni, for the very nice talk. Thank you very much. Are there any questions or comments, please? Please feel free to unmute yourself. Are there any questions or comments, please?
Okay. Hi, this is Rakesh from the University of Delaware. Very interesting talk. I just have a minor observation. So the non-local operator, if you look at the kernel, they're functions of 2n variables. It's like kxy. And your data is also a function of 2n variables. So you're really solving formally determined problems.
Yes.
These are pretty hard for the local cases, though. I mean, like in the n equals 2 case. So it's very interesting that you're solving formally determined problems here. That's all I just wanted to say that.
All right then. Yeah. I mean, that's an interesting observation. Thank you very much.
Okay.
Yeah. I mean, often, I mean, non-local stuff works. I mean, since we have this at disposition and very strong results to start with, like this UCP, often we can get, I mean, very strong results in turn, which are impossible in a local case.
Okay.
Thank you very much. Are there any other comments or questions, please? Any other questions or comments, please? Any other questions or comments, please?
Well, there need not be.
Yeah. Okay, if not, then thank you very much, Giovanni, for the very, very nice talk and for the very clear talk. Thank you very much. Thank you very much, everyone, for coming. Thank you very much.
Thank you. And let's take this occasion for saying happy holidays to everybody.